Hello everyone. So in this pre-lecture tutorial, we're going to be discussing how we can use the periodic table to actually help us understand trends in some critical atomic properties that we need to have a firm understanding of in order to understand how molecules come together, understand why certain elements react the way they do. And so really the easiest way to sort of figure this out is to consider how it is that effective nuclear charge varies in the periodic table. Now, what I mean by effective nuclear charge, I mean the positive charge that valence electrons experience as an attraction to the nucleus. Okay, so in order to sort of figure out how that works, we need to just do some common sense thinking about the periodic table. Now, again, if we consider the periodic table, we know that as we proceed from left to right within a period, right? So if I go from hydrogen to helium, or if I take the second period as I go to lithium, beryllium, boron, and so on, basically the atomic number increases by 1 unit for each element that I travel through a period as I go from left to right on the periodic table. So basically we know that as we travel from left to right, that the atomic number increases. And if you recall, the atomic number represents the number of protons in the nucleus of the atom. And so if the atomic number increases, that means that the positive charge increases as well. Okay, and if the positive charge increases, then that means the electrons are attracted more strongly. Okay, now what about as we travel down a group in the periodic table? And so whenever we assess these trends in atomic properties, we always want to know how the trend actually behaves going across the periodic table within a period and also going down a group. And as we go down a group, right, it's helpful to think of the Bohr model. Okay, if I'm within the first period, then basically I'm still in the first energy level. Okay, but if I move to the second period, then I'm in the second energy level. If I'm in the third period, then I'm in the third energy level. And basically what starts to happen is the electrons that exist in the outer energy level for each of these elements starts to get further and further away from the nucleus. And the further you are away from the nucleus, then the less attraction there's going to be between the nucleus and the electrons. And so you're going to feel less of an effective nuclear charge between those valence electrons and the nucleus. So basically, going down a group, the effective nuclear charge decreases. Okay, and if the effective nuclear charge decreases, then that means the attraction between the nucleus and the electrons decreases. Okay, and so now that we have this trend regarding effective nuclear charge sort of in our thoughts, it's a whole lot easier to understand how the other trends that are considered critical to the atom might behave as well. So let's consider atomic radius first. Now, in terms of defining what the atomic radius is, in simplest terms, basically it's the distance between the nucleus and the valence electrons. Okay, so basically if this is a nucleus and if my valence electrons are, say, here, then basically this distance from the nucleus to the valence electrons, that would be considered my atomic radius. However, keep in mind, because of the Heisenberg uncertainty principle, remember we can't actually say exactly where the valence electrons are. And so what's considered to be a more acceptable way to define the atomic radius is, let's assume that I have a hydrogen atom here. Okay? If I bond it to another hydrogen atom, then what that does is it obligates valence electrons to be in the space between the two nuclei. So between here and here, okay, there must be electrons there, and those electrons must be interacting in order to hold the hydrogen molecule together. All right, if I were to take that distance between the two nuclei and cut it in half, then half of this distance would also be considered the atomic radius. Okay, so basically the atomic radius is an indicator for how large the atom is. And so, again, if we move from left to right, going across a period, thinking back to what happens with effective nuclear charge, we know that the electrons are attracted more strongly, because as I go across a period from left to right, basically the atomic number is increasing by 1, the nucleus is getting more and more positive, and so that means there's a stronger attraction. So again, going from left to right, the nucleus gets more positive, and if the nucleus gets more positive, then that means that there's a stronger attraction for the electrons. And if there's a stronger attraction for the electrons, then basically the atoms must be getting smaller. As I go from left to right within a period of the periodic table. If I go down a group, then we're back in the same situation where I'm going to higher and higher energy levels. So if I'm in the first period, then my valence electrons would be here in the first energy level. But if I'm in the second period, then my valence electrons would be here in the second energy level. If I'm in the third, then I'm in the third energy level. And basically you can see as we're moving to higher and higher energy levels, then basically the atom is getting larger and larger and larger. And so as a result, as I go down a group in the periodic table, then basically atomic radius increases. Basically atoms get larger. If I go from top to bottom within a group of the periodic table. All right. Another important trend that we should look at is ionization energy, and this is strongly correlated to something that we call metallic character. What ionization energy is, it's the energy that is required to remove an electron from an atom in the gas state. Okay, so for example, if I had sodium and I managed to vaporize sodium, then if I apply some energy, the appropriate amount of energy, I should say, then basically I should get an electron to kick out from the sodium atom, giving me the sodium cation and an electron. Okay, so it's this process that we're referring to. As you can imagine, the more tightly held the electrons are within the atom, then the more energy is going to be required for me to remove an electron from that atom. If the electrons are held very loosely, then basically it should take far less energy for me to ionize that particular atom. And so applying that concept to periodic trends, again, as we go from left to right, remember that we have a stronger attraction for the electrons. Okay, and again, that's because the nucleus is getting more positive. And if the nucleus is getting more positive, that means the electrons are more attracted because positive charges and negative charges attract. And so as a result, it's harder to remove electrons as you go from left to right in the periodic table. Okay, and so if that's true, then basically ionization energy should increase as I go from left to right in the periodic table. Now, incidentally, again, we associate this tendency to form positive ions or cations with metals. And so if I have an atom that actually is easy to ionize, then that behaves more like a metal than an atom that does not ionize easily. And so if it gets harder and harder to remove electrons, then basically the elements that are on the right side of the periodic table behave less like metals. And so for that reason, we can also say that metallic character decreases as I travel from left to right in the periodic table. Now, again, we also want to consider what happens as I travel down in the periodic table. So if you recall, again, based on our discussion of effective nuclear charge, again, we're moving to higher and higher energy levels as we go down a group in the periodic table, making the valence electrons further away from the nucleus. And so if that's true, then those electrons experience a decreased attraction to the nucleus. So again, the electrons are not as attracted to the nucleus. For those elements that are further down in the periodic table. And so because of that, it's actually easier to remove electrons. And so if it's easier to remove electrons, then basically the ionization energy decreases, meaning it takes less energy for me to kick out an electron because those electrons are more loosely held within the atom structure. There's not as tight an attraction between the nucleus and the electrons. And so if it's easier to kick out an electron, then those elements behave more like metals. And so that means that metallic character increases going down a group within the periodic table. Okay, so now that we've sort of set the patterns within the periodic table, let's do a couple of example questions and see how we would apply this. Okay, so in this first example, I'm being asked for a set of 3 elements. Let's take this first set in 1A. I have lithium, carbon, and fluorine, and I'm supposed to rank them from the smallest to the largest atom in terms of atomic radius. So if I look at the periodic table, the first step is for me to actually locate those elements. So I've got lithium, carbon, and fluorine. Now, the first thing you should do is think about the set of elements you've been given and establish, okay, which ones are in the same group, which ones are in the same period. As it turns out, the 3 elements that I was given are all in the same period. And recall that within a period, basically, as I go from left to right, the atomic number gets bigger, which means the nucleus gets more positive, which means the electrons are more closely held to the nucleus because of that stronger interaction between the positive nucleus and the negative electrons. And so that means that the smallest atom in this list should be fluorine, and then the next largest should be carbon, and then the largest of this particular list should be lithium. All right, so again, basically, from smallest to largest, it should go this way. All right, with fluorine being the smallest, with the more positive nucleus, then carbon, then lithium. If I take a look at the second list, I'm being asked to do the same with lithium, sodium, and potassium. So let me go ahead and locate those in the periodic table. So I have lithium, sodium, and potassium. So now notice what's going on here is I'm working within a group. And within a group, as I move to higher and higher energy levels going down the first group of the periodic table, then I'm moving to higher and higher energy levels, which means that the atoms should be getting larger as I go down the group. And so that means that if I'm writing out this list in terms of the smallest to the largest, it should be lithium, then sodium, and then potassium. Now, let's consider ionization energy. Okay, so now I'm supposed to rank these elements from the lowest to the highest ionization energy. So basically, the element for which it's easiest to remove electrons to the one where I have the most difficulty. So I have magnesium, silicon, and sulfur. So going to the periodic table, I have magnesium, silicon, and sulfur. And so again, remember, just like when we thought about atomic radius, I need to think about what's going on with the effective nuclear charge. As we've said, as I go from left to right, the nucleus gets more positive, which means the electrons are more tightly held together, which means that the electrons of sulfur will be much more attracted to sulfur's nucleus than the valence electrons for silicon would be attracted for silicon's nucleus, and the electrons for magnesium would be attracted to magnesium's nucleus. And so what that means is the easiest of these atoms for which I can remove electrons would be magnesium. That would give me the easiest time. I would have to expend the least amount of energy kicking electrons out of magnesium. Then silicon, and then sulfur. Okay. What about this list? Right, from magnesium, calcium, to barium. So magnesium, calcium, and barium. And again, as we travel down the periodic table, basically barium is all the way towards the bottom of this group, which means that its valence electrons are in the highest energy level of the three elements that I'm given. The valence electrons for barium would be in the 6th energy level, compared to the 4th for calcium or the 3rd for magnesium. So if I have valence electrons in the 6th energy level, then basically what that means is these are electrons that are very far from the nucleus, comparatively speaking. And so if that's the case, it's easier to remove electrons from barium. Then calcium would actually have electrons in the 4th energy level, which would be closer to the nucleus, but not as close as the valence electrons for magnesium. So as a result, calcium would be the next easiest to remove electrons from, and then magnesium would be last. Okay, so go ahead and work on the follow-up assignment related to these periodic trends. Again, we'll be discussing these further in class, and if there are any questions, by all means email or bring up your questions in class. Okay, have a good night.